Let's start with the first presentation of the last session of today, which is about pattern recognition principles. And our first speaker is Varuna De Silva.
I will explain.
Okay. And the presentation, the title of the paper is Adversarial Contrastive Representation Learning for Passive Wi-Fi Fingerprint as of Individuals.
Yeah. Okay, thank you very much. My name is actually Rafael Pina. Unfortunately, because of unforeseen circumstances, the speakers cannot be present today, so they asked me to present on their behalf. So I'm going to present their paper called Adversarial Contrastive Representation Learning for Passive Wi-Fi Fingerprinting of Individuals. So basically, well, there is one problem many times, which is when there are certain indoor spaces, for example, sometimes it is a bit difficult to understand what's happening inside of them. So let's say, for example, that we have in the case of an hostage situation, for example, where we have hostages that are inside the building, and there is a special team that is trying to tackle what's happening inside that building, but they are not sure of the configuration of the building, they are not sure of how many people are inside. So if they are lucky enough, there might be cameras inside, for example, there might be other sources of information gathering that can help them to understand what's happening inside the building, how many people are there. But there are many cases where these problems happen in spaces that are unexpected, that no one is prepared to enter those spaces. So one very interesting idea that can be used to understand what's happening inside these spaces is to take advantage of certain waves that are in space. So for example, these can be radio waves, these can be Wi-Fi signals as well. So there are these signals that sometimes we are not thinking about them, but they can actually be useful for to track and to identify what's happening inside the unseen space. So as I was saying, for example, three very straightforward approaches are to use radio signals that might be present inside the building. So this can help us to understand if something is turned on, for example, or if anyone is using a certain device. Radar-based signals can be present as well in some cases. But one very interesting is the Wi-Fi activity signal, because nowadays we all have mobile phones with us, for example. So it is very common for Wi-Fi or mobile data signals to be activated. And because of that, we can take advantage of these signals to use two specific metrics that can be very useful to understand what's happening inside the space. So one is the channel state information, the CSI. So this metric is very informative, but it is also very difficult to get access to that indirectly, so without having access to the actual device. And then another metric is called the received signal strength indicator, the RSSI. So this one is not as informative as the CSI, but it can be accessed much more easily. So we can actually take advantage of this one in situations where it is not easy to have access to this information. So the idea that we want to explore in this work is actually, so is it possible for us to take advantage of this kind of Wi-Fi signals to understand what's happening inside of a building, for example? So if there is people inside the building, let's say in this example, so we have a building with several floors, there is people set in different areas of the building. Can we actually understand where these people are, for example, who these people are, what they are doing? So what we intend to do with this work is to investigate these possibilities through the use of the metric of the RSSI. So for that, we have used the dataset that is publicly available. So this dataset is called the UJ Indoor Lock dataset. So this dataset is quite complex, but very simply speaking, what this dataset consists of is about 3 different buildings that have 4 floors on each building, and it covers an area of almost 110 square meters, which is quite a lot. And inside these buildings, across all of them, there are 20 users using Android devices, from which this metric, the RSSI, was collected, and that's what's going to be used for us to conduct our experiments. So the most straightforward uses for this data set is to use all the information of the users to conduct either classification tasks for example, user identification, let's say, or it can be used for regressions as well when we are trying to understand where the people are based on the exact location, for example. So in our approach, what we intend to do is to not where they are, but to understand exactly who these people are. So we have, if we have an indoor enclosed space and we cannot see what's happening inside, how can we use the fingerprinting data of their Android devices to understand who they are exactly, so to identify the individuals. And so for our approach to achieve this, what we have done is to build a model that uses Siamese neural networks. So basically there are two different directions of that network that are going to receive the inputs. But the basis idea of our approach is to use something called contrastive learning, that for those who are not familiar with it, contrastive learning is very much about learning a model that can learn embeddings of the data, but assuring that the data, similar parts of the data are still similar in the latent space as well. So for example, if our model is encoding the inputs into a certain latent dimension, what contrastive learning wants to make sure is that even in the latent space, those samples are still similar. So that is on what we base our model of. So following these ideas of contrastive learning, we have devised these initial laws. So what this says is that, so let's say that we have a set of samples X, and we can define from that set of samples, we can define the input data, which we can call it sort of the ground truth. So that would be a part of the data that is the reference. And then the positive input represents what we want our latent space to be close to. So if we have a certain anchor, then our objective is to make the latent space close to that. And we want negative samples to be far away from that, because the point of contrastive learning is to ensure that similar samples are close in the latent space, and different samples are different in the latent space as well. So basically that is what this loss is doing, and that's our main objective. And we want to do this based on the RSSI data, as I was explaining earlier. And so to achieve that, we start with that basis loss, and we split our data set into two different sets, two subsets. The first one is based on the user ID. So what we want to do, which is the first part of our loss on the left side. So we apply the previous loss function to predict the data that corresponds to the user ID. And then we have a second set which corresponds to the space of the users. And for that, what we have defined is a certain beta, which is a regularization factor. That is basically because our main purpose is to find the identification of the users. So we have to adjust the other part of the data that is not directly corresponding to the ID of the users. And so this is these are the results that we end up with. So our loss converges to a small value after some epochs of training. And what's interesting is that, so as you can see on those cluster plots, on those clusters on my left side, we can see that, so this represents the latent space. So this is a TE-TSNE plot from the latent space that was learned. So we can see that we have a lot of clusters that are properly defined. So it means that our latent space is actually learning the differences between different users. So we can see that features of different users, they are clustered in the same space most of the time, with some exceptions on the other side, but that can be because of the complexity of the data as well. But mostly we can identify some pretty well-defined clusters, which is pretty interesting. And so that is the representation of our latent space. But when it comes to the performance of the models, so the idea is to encode the data of the RSSI data to understand who the users are inside the building. And then based on those embeddings of the latent space that I was showing you before, what we do is that we use a model that receives those embeddings as an input, and it is going to predict who the users are. So when we do that, we can have a pretty high accuracy. So that is based on this first table on the top left side. And so when we try to predict the user ID, we have a high accuracy. But then if we try to predict the location, we can see that the accuracy comes down quite a lot. But that makes sense because our objective is to predict the user ID. So it's to predict who the people are inside the building, which means that our model can actually differentiate in latent space the user IDs from the locations, from the places where they are. And then this is just to, the last table is to validate the fact that, so if we use the latent space, we cannot predict the location, but we can predict the user ID. But if we use the raw data, we can predict location, which means that our latent space can make the difference between user ID and location of the people. So as a conclusion of this work, so sometimes we have situations in indoor buildings, for example, hostage situations where we cannot see what is happening inside the building, but we can take advantage of Wi-Fi signals from our mobile phones, for example, to understand who the people are inside that building and where they are. And that is what we have explored in this paper using a model based on contrastive learning. And one important factor is that there is not many data sets that explore these kind of problems, so it is important to explore more of these types of data sets in the future. Yes, thank you very much. If you have any questions, I'm happy to answer.